Okay, in this lecture we're going to talk about fixed points and functional iteration. We do some cool theory which will kind of encapsulate what we've done previously. And the idea start out, we have a sequence defined in this fashion that xn plus 1 is equal to f of xn. And all we know at this point is that f is some sort of a function. This process is called functional iteration. Now suppose that this sequence of points xn actually approaches a limit s. Okay, and now do some extra assumption on this. Assume that f is continuous. That's not too much to assume. Then what do we know? Well, f of s is f of the limit of xn, and since f is continuous, we can swap out our limit of xn with f, and so f of xn is equal to n plus x sub n plus 1, when that's just a subsequence of my previous sequence, so it will converge to the same point. And so my f of s is equal to s. This means that this point s is a fixed point of my function f. Okay, now let's look at little f. Little f is a function, and we can define our big F as x minus f of x over f prime of x. And if we do define our f in this way, this will give us Newton's method. Okay, now we say that f is a contractive mapping if the absolute value of f of x minus f of y is less than or equal to lambda times x minus y for all possible choices of x and y, where 0 is less than or equal to lambda, which is strictly less than 1. So the idea here is that this function f will make its points go closer together. Okay, so the contractive mapping theorem will say, let C be some closed subset of the real line. If f from C to C is a contractive mapping, then f has a unique fixed point. Moreover, this fixed point is the limit of the sequence xn, where xn plus x sub n plus 1 is equal to f of xn, and x sub 0 is any point of C. So the contractive mapping theorem says, hey, this iteration is going to converge. Okay. Alright, so let's prove this. Let's start out and let's consider x sub n plus 1 minus x sub 0. Okay, we can realize this difference, okay, as a telescoping sum from k equals 0 to n of xk plus 1 minus xk. So we've got minuses attached to some of the xk, or the xk half of the time, and pluses attached to the xk the other half of the time. Everything in the middle goes out and leaves us with this right here. Okay, so I can now take that and I can realize my x sub n plus 1 as x sub 0 plus this telescoping sum. Okay, now take a look at the absolute value of xk minus xk plus 1 minus xk. Well, this will be equal to the absolute value of, and here, oops, this should be a k here, and this should be a k minus 1. It's close enough for jazz, though. This will be, by the contraction mapping theorem, this will be equal to lambda times x minus x sub k minus 1 minus x sub k. This will, going down in this same fashion, we can get that this difference xk plus 1 minus xk is equal to lambda to the kth power times this constant number. Okay. So in this way, we can write this telescoping sum. Okay. And let's see. This should be a less than or equal to here, guys. Anyway, we can write this first step. We go by the triangle inequality. Then we apply the stuff we did before, just on the previous slide. Here we've got this constant. We can factor it out. Hey, this is just the geometric series over here. So I have this absolute value of difference bounded above by this fixed sum. Okay. It follows that this telescoping sum converges because it converges absolutely. Why does it converge absolutely? Well, it's bounded. This converges, okay, because it's bounded above by this. Okay, it's a sequence of positive terms bounded above. All right, so. And so, therefore, we get that my limit of my xn is equal to this infinite sum here, and this infinite sum exists. Okay. So, denote the limit by L. Okay. Now, suppose that y sub 0 is an element of C, and we define my sequence y sub n recursively as usual, and we take the limit equal to of my yn equal to m. What we can see here is that my the absolute value of L minus m is equal to the absolute value of f of m minus f of L minus f of m, and which is less than or equal to this difference right here, and this can only be true if L minus m is equal to 0. So if L and m are different, it gives us a contradiction. Okay, so let's look at an example here. Let's take x sub 0 as negative 15 and define x sub n plus 1 equal to 3 minus 1/2 of the absolute value of xn. Okay, so looking at this, I can say, hey, have my function f of x be equal to 3 minus 1/2 absolute value of x. Okay, replace the x with the y, and let's see what this is. My f of x minus f of y is equal to 1/2 of the absolute value of f of y minus x. Switch these guys around and we get something similar, and so we can say that the absolute value of the difference between these two is equal to 1/2 of the absolute value of x minus the absolute value of y, which is less than or equal to 1/2 of the absolute value of x minus y. So this function f is a contractive mapping, and so this guy is going to converge. Okay, and so that does it.